So in complex number, we have now been left with only one concept, which is the rotation theorem, Okay. In some books, they call it as the Coney method or the Coney rotation formula. Okay. So all of you, please pay attention. This is one of the concepts which is asked primarily in JEE main and advanced exams, not that much in your regional entrance exams like CET and PaySat, etc. It's more of a subject matter of JEE main and JEE advanced. Okay. So what is this theorem all about? Let us first see the theorem and when it is applicable. So let us try to understand this theorem. Now, let us say this is your Argand plane. Okay, this is your Argand plane. Okay. On this Argand plane, there are three complex numbers. Let me choose them as, let's say, Z1. Let's choose a Z2 complex number here. And let's say another complex number here, Z3. Okay. And these complex numbers are so positioned that this angle here is theta. This angle here is theta. Okay. So this rotation theorem is basically a theorem which connects Z1, Z2, Z3 and this theta with each other. Okay. So let us try to understand what is that theorem which connects Z1, Z2, Z3 and theta. Okay. So the theorem goes like this. Z3 minus Z1 by Z2 minus Z1 is equal to modulus of Z3 minus Z1 by modulus of Z2 minus Z1 e to the power I theta. Okay. Now I'll be proving this theorem, not to worry. So we'll prove this theorem in some time. But please understand, for proving this theorem, you would have to recall your argument of Z1 minus Z2. Okay, so how many of you actually remember how to find argument of Z1 minus Z2 on the Argand plane? Say me if you already know it. Or nobody is saying that. Okay, never mind. I will discuss that. I will in fact revise that. And then I will come to the proving of this particular theorem. Right? So how does this theorem come about? This theorem comes from your very simple understanding of Euler's form and argument of difference of two complex numbers. Okay. So basis of both these concepts, this theorem is evolved. Okay. So let us quickly revise. Let's quickly recap. How do we find argument of difference of two complex numbers? Okay. So let's say I have two complex numbers, Z and W. Okay. I want to find out the argument of Z and W, given that I know they are located on the Argand plane at these positions. So let's say this is my Z and this is my W. Okay. So how do you find out? Anybody can guide me if anybody remembers. How do you find argument of Z minus W? No? Okay. Anyways, do you remember how to find the angle between two vectors? Angle between two vectors? Okay, let's say if I have a vector like this and I have a vector like this. Okay, vector A and vector B, right? What is the angle between these two vectors? You will say this is the angle between the two vectors. Yes. So angle between two vectors are found out when they are made co-initial. Co-initial means their tails are connected to each other. Absolutely right. Okay. Now you have to do the same thing over here. But in our case, one vector will become your positive real Z axis. Okay. and the other vector will become a vector starting from W going towards Z. That means WZ vector. Okay. And starting from positive real Z axis, you have to give a direction to this angle. Because in our case, in case of a vector, we don't put any direction to that angle, right? Angle between two vectors is always mentioned as a magnitude. But for our argument, we need to mention this direction, and that direction will be decided from the positive real Z axis towards that WZ vector. Okay. So coming to this particular diagram, if I make the WZ vector, it will look like this orange line, right? And this is already positive real Z axis. So what is the angle between them? If you just extend it a little backward, this is the angle that we are referring to. And remember, I have to take from positive real Z axis till I hit WZ. So this angle will be called as the argument of Z minus W. I hope this small discussion helps you to recall this concept, right? Okay. So let's come back to our given figure. Meanwhile, anybody has any questions, any concerns here? Any questions, any concerns? Okay, let's come back to the figure. Let us say I make some small constructions here. Let me extend this slightly backward and let's call this angle to be angle alpha. Okay, let's say I call this to be angle alpha. Let me write inside here. Yeah. And let me extend this slightly backward and let's call this angle to be angle beta. Okay. And if this is theta, of course, this angle will also become a theta. I'm writing inside in the figure. Fine. Now, let us write down Z3 minus Z1 in the Euler's form. Now, whenever you write a complex number in the Euler form, what do you write it as? R e to the power I theta, right? Where R is what? The modulus, correct? And theta is what? The amplitude or the argument, isn't it? So, can I write Z3 minus Z1 as modulus? Modulus is as good as saying modulus of Z3 minus Z1. Correct. So what is modulus of Z3 minus Z1? Modulus of Z3 minus Z1. Right. And what is the argument of Z3 minus Z1 as per this diagram? As per this diagram, tell me what is the argument of Z3 minus Z1? Mention on the chat box. Absolutely right, Saket. It's beta. Yes. Yes. Let's call this as equation number 1. Let's call this as equation number 1. Okay. Now, in the similar way, I would like to know from you that can I write Z2 minus Z1 as mod Z2 minus Z1 e to the power I alpha? Yes or no? Because now alpha will act like the argument. Yes or no? Now let's divide 1 by 2. Let's divide 1 by 2. If you divide 1 by 2, what do you end up getting? You end up getting like this, Z3 minus Z1. So I'm taking the left side and dividing it by the left side of 2 equal to mod of Z3 minus Z1 divided by mod of Z2 minus Z1. Okay. And of course, you have e to the power I beta divided by e to the power I alpha. Correct? Now, may I write this as beta minus alpha directly here without wasting much time? Yes or no? Now come back to the figure again. Tell me, what is beta minus alpha? Tell me beta minus alpha. Beta minus alpha. Can I say that will be theta itself, isn't it? So beta minus alpha, that's nothing but beta minus alpha, that is nothing but theta, isn't it? Because beta is the opposite exterior angle, correct? So opposite exterior angle is equal to the sum of the two interior angles, isn't it? Correct? So in light of that, I'm going to replace my beta minus alpha with a theta. And there you go. This is the formula that we wanted to prove. Okay, this is the formula which we wanted to prove. Is this fine? So this formula is not coming from sky. This formula is not out of the box formula. It is basically trying to reinforce our understanding of argument of difference of two complex numbers, and of course it is using Euler's form, right? So it's a mix of those two combinations, right? Now many people ask me this question, sir, why do we call it as a rotation formula? Because see, it basically, when you remember this formula, I'll just give you a small mnemonic. It just appears as if you are trying to rotate it like this, right? Some kind of a rotation is happening. That is why it is called rotation formula. And many times it will help you to figure out what is the new position of a complex number if it is rotated about a given point by a certain angle. And of course, you can, change its length also. Okay, we'll see it through some questions. Okay, any questions in the derivation of this result? Any questions in the derivation of this result? I hope you have all copied this down. Clear, everyone? Great. Now, the very same formula can also be written like this. Okay, there are certain books which will write it like this: Z2 minus Z1 upon Z3 minus Z1 equal to mod Z2 minus Z1 upon mod Z3 minus Z1 e to the power minus I theta. Mind you, both of them are same expressions, just they are reciprocals of one another. So you have done nothing to this formula. You have just reciprocated your LHS. You got this. You reciprocated your RHS. You got this. Okay. Mind you, the two formulas are the same formulas. I am not giving you any different formula here. Both are same formula. Okay. Many people ask me, sir, why do you give two versions of the same thing? Is it necessary to know both of them? Yes. In solving few problems, you never know which of the two form would be required for which purpose. Okay. That is why I normally give both the versions of the formula. Okay. Note it down, and then I will tell you a mnemonic to remember this. Because many people say, sir, I tend to get confused when to take a theta and when to take a minus theta. Okay. So for that, I have made a mnemonic. I have made a memory aid so that you can remember this rotation theorem. Okay, note it down, everyone. Okay, so let's take a memory aid or a memory assistant. Memory aid for remembering the rotation theorem. Now listen to this very, very carefully. Normally, you will be given a situation where there would be three complex numbers involved, right? And one angle will be given to you. For example, in our previous discussion, we were given Z1, Z2, and Z3, and we were given this angle. Okay. Now, in order to recall this formula, first assign a direction to this angle. Of course, this angle will not be given with a direction. Angle's magnitude will only be known to you. It is up to you to decide a direction for it. For example, if you decide to give it an anti-clockwise direction, let's say this is an anti-clockwise direction, right? Now, this is what I call as the head of the arrow. Okay, this is the head of the arrow, and this is the tail of the arrow. Correct? Now, in order to recall the rotation theorem, this is something which I had invented when I was, preparing for these exams. So whichever two complex numbers are attached to the head of this arrow, write them down, writing this complex number in the second position. That means I normally call this as a hinge. So let's say this is the head of the arrow, right? So these are the two complex numbers linked to the head. So write it as Z3 minus Z1. Okay, so hinge should always be the one after the negative sign. Correct? Now, what are the two complex numbers connected to the tail of this arrow? Z2 and Z1. So I write it down as Z2 minus Z1. Correct? Put an equal to sign. Write the mod of these two guys here. Okay. Then write e to the power I. Just write a theta if you have taken an anti-clockwise direction. So here, as you can see, this direction was anti-clockwise, isn't it? ACW, anti-clockwise. So when it is anti-clockwise, just keep it as theta. Okay? Or a plus theta, whatever you want to call it. Now, if you want to give the arrow a clockwise direction, then see what will happen. So again, I'm reproducing the same figure. Okay. Now this time, this angle theta, I'm giving it a clockwise direction. Now remember, this is your head. This is the head of the arrow. And this is the tail of the arrow, correct? So what I do in this case, again, same thing. Whichever two complex numbers are connected to the head, write them first. And hinge should always be after the negative sign. So hinge, this is your hinge. Okay. Hinge is basically a point where we are assuming that some kind of a rotation is happening. Okay. It is just an assumption that it is getting rotated like that. Okay. Divided by Z3 minus Z1. That means the two complex number connected to the tail of the arrow. And always write the hinge after the negative. Equal to mod of these two guys. Now, since you have taken the direction as clockwise, you will write minus I theta. And mind you, this yellow one and this white one, both are same things. So just because you have taken clockwise, anti-clockwise, the theorem has not got changed. The theorem is the same. It is just helping you to recollect the theorem. That's it. Okay. So it is just helping you to recollect the theorem. Is it fine? Have you all understood this memory aid? See, it is up to you. You make your own way to remember things. If you have your own personalized way of remembering it, go for it. This is what I used to follow, and hence I'm just sharing it with you all. You can have your own sweet way to remember these formulas. Okay. Now, time to look into some questions. Let's see some questions based on this concept. Shall I move on to the next slide? Okay. A very simple question I would like to begin here. Let us say I have a complex number. I have a complex number Z. Okay. I have a complex number Z. Now, what I'm doing with this complex number, I am rotating this complex number about origin. Okay. I'm rotating this complex number about origin in an anti-clockwise fashion. In an anti-clockwise fashion till I reach 90 degrees. Okay. Mind you, when I'm rotating it anti-clockwise by 90 degrees, I'm not changing this length. So this length and this length is same, right? Now, assume that this complex number which I reach is Z1. Find Z1 in terms of Z. That means find how is Z1 and Z related to each other. Question is clear to everyone? Question is, again I'll repeat, there is a complex number Z, right? So what I'm doing with this complex number, I'm rotating this line OZ anti-clockwise by 90 degree, so that this Z now comes to a new position Z1. Okay. But mind you, when I'm rotating it by 90 degree, I'm not changing this length. So what is this complex number Z1? Okay, Pratik, I'll make your life easy. Let us say I want Z1 by Z represented as a complex number. Okay. Let me change the question. Z1 by Z is a complex number. Find A and B. Saket, absolutely right. Your result is absolutely correct. See, very simple. Very simple. If you see, I'm applying the rotation theorem or the Coney method at this as a hinge. Okay, so consider this to be a hinge. So your 0 is your hinge. Correct. And let us write down the Coney rotation formula over here. I have already given a direction to it, which is anti-clockwise, so we'll follow that itself. However, it doesn't matter. Even if I had given this same 90 degree clockwise direction also, the result is not going to change because of that. Okay. So now this is the head of the arrow. This is the tail of the arrow. Correct now? Write down the two complex numbers connected to the head first. So Z1 minus 0. So origin will be considered to be 0. Okay. Hinge should always be after the negative sign. Divided by Z minus 0. That means the complex numbers connected to the tail. This is be equal to mod Z1 minus 0 by mod Z minus 0 e to the power I plus pi by 2, because you have considered an anti-clockwise direction for it, isn't it? Now this is as good as saying Z1 by Z. Now this is mod Z1. Mod Z1 is this length. Let's say I call this as R, and this will also be R. So mod Z1 will be R, mod Z will also be R. E to the power I pi by 2. So R gets cancelled. So Z1 by Z becomes e to the power I pi by 2. Which complex number is actually e to the power I pi by 2? Or let me be more precise, 1 e to the power I pi by 2. Which complex number is 1 e to the power I pi by 2? Write that complex number in the point form. One e to the power I pi by 2 is which complex number? Right, it is I. Absolutely. So basically, I wanted to hear this result from you all, that your Z1 is IZ. Okay. In fact, if you want to solve this question, then this will be 0. This will be I into 1. So A is 0 and B is 1. Okay. Now, this is a very important result actually, that many of you should be noting it down here. Note, if any complex number is multiplied by I, then the complex number gets rotated by 90 degrees anti-clockwise. Anti-clockwise. Or you can say moves to a new position which is at a 90-degree anti-clockwise location without changing the modulus. Without change of the modulus. Is it fine? Any questions? Any concerns? Is this fine? Okay. So let us take another question based on the same. I hope all of you have copied this down. Okay. Let's take another question on the same. Question is, prove that the area of triangle whose vertices are z, omega z and z plus omega z, omega being the cube root of unity. Okay, I hope you all recall that omega was what? Omega was minus half plus I root 3 by 2, right? Also written as 1 cos 2 pi by 3 plus I sin 2 pi by 3. Okay. Also written as 1 e to the power I 2 pi by 3. Okay. So this is the point form, polar form, Euler form. So prove that the area of the triangle becomes root 3 by 4 mod z square. Let's see whether you are able to crack this. This question can easily be solved just by using our previous concept. Now see, everybody please pay attention. Let's say this is my z. Okay. So let's say this is my z. Okay. And this is your mod z. Right? Now who will tell me where will be omega z located? If I have to locate omega z, what should I do to get omega z? Tell me. See, very simple. Let's say if z is mod z e to the power I theta. So let's say this angle was theta. This angle was theta. When I'm multiplying omega to z, what am I doing? I'm multiplying 1 e to the power I 2 pi by 3 with mod z e to the power I theta. Now, mod will get multiplied. So 1 and this will get multiplied. That will give you mod z. And what will happen to the e power will now become theta plus 2 pi by 3. So what does it mean? It means mod z omega or omega z is located at the very same distance from the origin. That means this length is same as this length. So this is also mod z. But now this angle is further more by 2 pi by 3 or 120 degrees, isn't it? Right? So basically a rotation has happened. Are you getting my point here? Correct? So this is something which we had already started learning when we were doing our multiplication of vectors, multiplication of complex numbers. Are you able to recall that multiplication concept? Similar thing was happening. Okay. Now, we have already located, of course, z, we had to choose one z. So we have already located now omega z with respect to that z. Now, where will be z plus omega z? Can I locate that also? Now, that is pretty simple. What do you do to find out the sum of two complex numbers? Right, you complete a parallelogram. Absolutely right. We complete a parallelogram, and this is where your z plus omega z will be lying. Am I right? Any questions? Any questions? Okay. I hope my parallelogram is looking like a parallelogram. Once again, maybe I'll draw it more accurately. Yeah, now it is looking like a parallelogram. Yeah. Okay. So now, what have you been asked in the question? What have you been asked in the question? The question is saying that if you make a triangle connecting z, omega z and z plus omega z. Okay, that means this is your triangle. I'm drawing that in blue color. This, this, and this. Right? Yeah. So what are they asking you for? They're asking you for the area of this triangle. Please find it out now, everybody. Take 2 minutes. Find the area of this triangle. And just say done if you are done. However, the result is already mentioned on your screen here. Okay, let's solve it together. Can I say this figure is actually a rhombus because all these sides will be of mod z length, isn't it? Correct? All right. Now let's connect this, or let's make a diagonal from origin to z plus omega z. We all recall that this angle will be a 90 degree, correct? Okay. Now this is going to be a 60 degree angle, correct? This is going to be a 30 degree angle. Anyways, we just need one of them. Now, if I want to find the area of the triangle, let me name it ABC. I need to know its base and height, which I can easily find out. So what will be the base of the triangle? What will be the base of triangle ABC? What will be the base of triangle ABC? Now see, this is mod Z, right? And this is 30 degree. So the base of the triangle will be mod Z cos 30 degree into 2. Yes or no? What will be the height of the triangle? What will be the height of the triangle? Height of the triangle will be mod Z sine 30 degree. Yes or no? So what will be the area of this whole triangle? The area of the triangle will now be half base, by the way, cos 30 is root 3 by 2, into height. So that will lead to you getting √3 mod z square by 4. Okay. So this is what is our answer to this question. This is what we wanted to prove it. Done. Is it clear? Any questions? Any questions? How did you get? Okay, now see. This is how much? 120. This will also be 120. And we know all these angles, opposite angles will be equal here. This will be 120. So 120, 120, 240 gone. So out of 360, 240 is gone, Vikram. How much is left?
Oh, yes, sir. Got it. Yes, sir. 60 and 60 is a
60 and half of. Area is not a complex number. No. Area is not a complex number, Raj. Area is a real number here. But here, you are finding out the area of the triangle on the Argand plane, which is made by these complex numbers. Okay. So the complex numbers are creating a real triangle, right? And you are trying to find the area of that triangle. Let's take the last question of this topic before moving on to the concept of limits today. This is one of the very important questions also which is asked. So we'll not only solve it, but we will also remember the result. Okay. After solving, we'll keep this result in our mind as well. So read the question. It says, complex numbers Z1, Z2, Z3 are the vertices of triangle ABC respectively of an equilateral triangle. So I'll make the figure here. We have to prove that these three affixes or these three complex numbers are related to each other by this relationship. How do you solve this question? Okay, let me help you out here. I know most of you will be wondering where to start from. See, choose one of the affixes, choose one of the vertices. Let me call a person's name. Maybe Krish Das. Choose one of the vertices. Which vertex you want to choose? Any vertex. Okay, so Krish has gone for B. Okay, now Krish, just answer this simple question. What is this angle here, Krish? Oh, it's an equilateral triangle, mind you. So what is this angle here, Krish? 60 degrees, correct, pi by 3. Okay, fine. Now, considering B to be the hinge, since Krish has gone for this angle is 60 degrees or pi by 3. Okay, now again, Krish, back to you. Give a direction to this angle. Any direction you want, clockwise, anti-clockwise, it is up to you. Which direction you want to give? Anti-clockwise. Okay, so Krish has given an anti-clockwise direction. Now, assuming that this angle has been taken in an anti-clockwise direction, this magnitude of the angle is pi by 3 and the hinge is there at B. Can we write Coney at B? So write down the Coney rotation formula at B. So what would you write? First, which are the two complex numbers connected to the head of the arrow? This is the head of the arrow. So Z1 and Z2 is connected to the head of the arrow. So write Z1 minus Z2. Mind you, the hinge is at Z2. So hinge should always be the second one. Okay, after the minus sign. Okay, don't write Z2 minus Z1. Divided by, this is the tail of the arrow. Which are the two complex numbers connected to the tail? Z3 and Z2. So I will write here as Z3 minus Z2. Okay. Now mod Z1 minus Z2 by mod Z3 minus Z2 e to the power. Now since it was anti-clockwise assumed by Krish, so he will write I pi by 3. Is that fine? Any problem in creating this rotation theorem formula at B? Now, please note, since this is an equilateral triangle, mod Z1 minus Z2 will be equal to mod Z3 minus Z2. Right? Because this triangle is an equilateral triangle. Right? What is mod Z1 minus Z2? Distance between Z1 and Z2, right? So this distance and this distance are equal. So what will happen? These two will get cancelled out because they're equal in length. So in light of this, can I say this expression boils down to Z1 minus Z2 divided by Z3 minus Z2 as e to the power I pi by 3. Okay. Let's call this equation to be our first equation. Any problem with writing the first equation? All fine. Very good, Krish. Now let me take somebody else's name. Nikita. Nikita, choose any other vertex. So Krish chose B. Now you have A and C remaining. Which one you want to choose? Okay, so Nikita has chosen vertex number A. Okay. So now my hinge has shifted to vertex number A. So this is my hinge point. Let me erase this so that you don't get confused now. Yeah. Now this angle is again a pi by 3 angle. Now Nikita, please assign a direction to this angle. Whether you want to take clockwise, anti-clockwise, which direction you want to take. Okay, for a change, and good that you have taken a different direction. So for a change, Nikita has taken a clockwise direction. Correct? Now let us write Koni at A. Now this is my head of the arrow. So first write down the two complex numbers connected to the head of the arrow. Mind you, since the hinge is at Z1, you will write Z2 minus Z1. Okay. Hinge should always be after the negative sign. This is the tail of the arrow. Correct? So tail of the arrow connects Z3 and Z1. So write this as Z3 minus Z1. Again, mod of these two guys. E to the power. Now, mind you, since the direction was taken as a clockwise by Nikita, this will become minus I pi by 3. Minus I pi by 3. Correct? Yes or no? Now, since this is again an equilateral triangle, these two will get cancelled out because they are of same length. Now, what do you get from here? We get Z2 minus Z1 by Z3 minus Z1 e to the power minus I pi by 3. This is my second equation. This is my second equation. Okay. Now, having got 1 and 2, can I do something with 1 and 2 so that I get this particular show that condition? Okay. In short, can you do one thing? Can you do something to eliminate this e to the power I pi by 3 from both the positions? You say, sir, simple, multiply 1 and 2. Correct? Because on multiplication, e to the power I pi by 3 and e to the power minus I pi by 3 will cancel each other out because they are reciprocals of one another. Correct? So when you multiply, what do you get? You get Z1 minus Z2 by Z3 minus Z2 multiplied with Z2 minus Z1 by Z3 minus Z1. So LHS, LHS I am multiplying. RHS, RHS if you multiply, what happens? they will cancel each other out and they will actually become a 1, isn't it? Okay. Now, multiply these two together, and take this to the other side. That means I'm asking you to do this operation. Okay, I'm just writing everything in a much detailed way. Of course, I'll be simplifying it now. Is it fine? Any questions? Okay. By the way, this is as good as saying Z1 minus Z2 square with a negative sign. Okay. Here also you can square it up. Sorry, you can multiply it up. This will become Z3 square. This will become minus Z1 Z3. Then minus Z2 Z3 plus Z1 Z2. Okay. Let's expand this side also. So this will become 2Z1 Z2 plus minus Z1 square minus Z2 square equal to Z3 square minus Z1 Z3 minus Z2 Z3 plus Z1 Z2. So one of the Z1 Z2s will get cancelled off. Now collect these two guys on the right side and collect these guys on the left side. Okay. I'm not going to show these arrow sign because they are killing my space. So ultimately what I'll get Z1 square, Z2 square, Z3 square because I've taken these two to the right side. Okay. And I'm writing the right side first. And I take minus Z1, Z3 minus Z2, Z3 on the left side. So I'll be left with, there's already a Z1, Z2 waiting there. There you go. This is what we wanted to show. Any questions, any concerns? So these are the type of questions you can solve very easily by using your Coney rotation theorem, right? So with this, we end this chapter. Okay, 3 smileys to indicate that we are closing this chapter.